So that's the end of the slides. So we'll now go and actually do this run. So let's try to do that. We're going to go to the, not to the xmean.py, but to the parallel k-means.py. And we're going to do that and see what happens. Should produce 8 plots if we're lucky. Takes a little while because unlike some of our code, it's actually doing something non-trivial. It's generating Gaussians and then doing clustering with them and things like that. And here they are, they're plopping up. They took a little while to get going. So what we'll do, we pop this program popped up 4 files. Let's just see what we have. This we run with iterations 1. So this is actually trying to get funny answers. And maybe we can make this a little bigger so you can see what's going on here. So here we have k equals 8. Parallelism of 1, everything is parallelism 1 here. Max mean of 1, so we're doing the mean distortion as the criteria, 1 iteration. And here we have the large radius, which is, remember, the small, large, and very large. And here we managed to have 1 cluster that bled between these 2 at the top. This one here is therefore sort of 2 here, and a bit of this one. This one is 1 here, and a bit of this one. This one got broken up into 2, and this one got broken up into 2. So probably not the global optimal, but it's sort of okay. Although it doesn't look as pretty as some of the solutions, so that's that one. Now we have, what's the next one we pop up here? K equals 4. For the very large case, we have a good solution. It looks near the, we notice again these clusters bleed a bit into each other. That's just due to that's what happens with the very large case. The radii are such that they tend to have slight overlaps. And I would say this solution looks near the global minimum. Now we have k equals 2. This one looks, again, this one looks pretty normal. We join these two generated clusters into one found cluster. These 2 generated clusters are another found cluster. So that's what you'd expect for near the minimum. Here we have k equals 4. 4 clusters in the small radius case, and we got what we might have hoped. Each of those clusters, each of the generated cluster becomes 1 found cluster. So that one ran okay even with 1 iteration. So it's essentially optimal. Now remember, this is the one we discussed. The k equals 2 clusters with the smalls, and we said there were 2 types of solution. This one has come with the intuitive solution, which is possibly not mathematically the best, because the other solution, which is 1 and 3, had mathematically a slightly smaller mean value. And this one has come up with the one that you'd expect to get, and what you get if you change this to max mean of 2, which is to select maximum as the quality criteria. Now we have k of 6 on the large case. So this is actually pretty reasonable. For k equals 6, we've taken the 2 top clusters, which are actually the larger ones, we've chopped them into 2, and we've taken the 2 bottom clusters and kept them as 1. So this is probably the optimal solution for this problem. So even though with iteration of 1, you found the right answer. Again, there's almost certainly ambiguities. You could probably, there might be other solutions with the exact division of the top cluster into 2 being done in different ways. Either this division line here rotating or this division line here rotating. Here we have the large radius case. Okay, 4 clusters, and it's given a pretty good answer here. Again, looks near the optimal. So this run actually ends up being, having no really peculiar answers. Here we have the large radius, 2 cluster case. We join these two in a pair and these two into a pair. So that's pretty reasonable. Well, again, what you'd expect. I mean, whether it's these two joined and these two joined, or these two joined and these two joined is hard to say. But to take the 4 generated clusters, and when you do 2 clusters, to do them in pairs is a reasonable thing to do. So there we are. You can go and play forever with this, and you can actually have a lot of fun playing around and taking various scenarios with generated clusters. I mean, it is worth noticing how easy it is to generate clusters if we want to look at that code. Let's see if we can find that code here. It's really simple. Let's look at the parallel k-means.py, the top code. We're not going to go into in these lectures, actually actual Python. We'll go into it more when we look at the parallelism. But let's look and see how we generate random numbers. Well, we just what is all right? So we set tot to be 1,000, 250 by 4. That's the total number of points we want. And here we generate a 1,000 values for y, x random, 1,000 values for y, which is y random, and the rand n is the Python function that generates a number, but a random number, which is Gaussian distributed with a radius of 1, namely with a standard deviation of 1. We take these numbers and multiply them by the radii we want, and then we then take those points generated with mean of 0 and standard deviation 1, so they're actually positive and negative. We multiply by their radii and add them to the centers, and that gives us the data. So generating these 4 clusters is just this code here, is particularly easy to do. Okay, so that's the end of this lecture. We will discuss MapReduce briefly in the next lecture, and then after that we'll come back to this Python example and show how we can write it in a MapReduce-like syntax and illustrate parallelism, although we don't actually run it in parallel. We just, instead of running, when you run in parallel, you have multiple map jobs, say, running at the same time. We will just run multiple map jobs and show that we can do that and get the same type of algorithm. So that's the end of this lecture. Thank you very much.